The rise of language machines, or large language models, is revolutionizing the field of artificial intelligence. These sophisticated computer programs are trained on massive datasets of text and code. This allows them to understand and generate human-quality text in response to a wide range of prompts and questions. From crafting creative stories to translating languages, LLMs are showcasing the power of AI to interact with and process human language in unprecedented ways. The significance of LLMs lies in their ability to bridge the gap between humans and machines. They can be used to automate tasks, provide information and entertainment, and even assist in research and development. This has far-reaching implications for various industries, including customer service, education, healthcare, and more. As LLMs continue to evolve, they promise to reshape the way we live, work, and interact with technology. However, the rise of LLMs also presents challenges. Ensuring their responsible development and deployment is crucial. Ethical considerations such as bias mitigation, transparency, and accountability need to be carefully addressed. The future impact of LLMs hinges on our ability to harness their potential while mitigating potential risks. Inside the language engine, at the heart of powerful LLMs like ChatGPT, lies a revolutionary neural network architecture known as the transformer model. Imagine a network of interconnected nodes, each representing a small unit of computation. These nodes are organized into layers, and within each layer, the magic of attention takes place. The transformer model doesn't process language sequentially like humans reading a sentence. Instead, it considers all words simultaneously, weighing their importance through this attention mechanism. Imagine you're trying to understand a sentence. You don't just focus on individual words in isolation. You consider the context, the relationships between words, and their order to grasp the meaning. Transformers mimic this ability. Each word in a sentence is compared to every other word, allowing the model to understand relationships and dependencies, even long-range ones. This parallel processing and contextual awareness give transformers a significant edge over previous architectures. Within these layers reside countless artificial neurons, interconnected pathways that process and transmit information. These neurons, inspired by the biological neurons in our brains, are the building blocks of the LLM's understanding. By adjusting the strength of connections between neurons, the model learns to identify patterns, relationships, and meaning within the vast sea of data it's trained on. Teaching a machine to speak, the journey of transforming a collection of interconnected nodes into a language-proficient AI, is a complex and computationally intensive process. It all begins with pre-training, where the LLM is exposed to a massive dataset of text and code. This dataset acts as the model's textbook, exposing it to the nuances of language, grammar, and even factual information. Think of pre-training as providing the model with a vast library of books to read. Through this exposure, the LLM begins to develop an understanding of language structure, common phrases, and even world knowledge. It learns to predict the next word in a sequence, translate languages, and answer questions based on the information it has absorbed. However, pre-training alone is not enough to create a truly versatile and capable LLM. This is where fine-tuning comes in. During fine-tuning, the model is trained on a more specific dataset, tailored to the specific tasks it's meant to perform. This could be anything from writing different kinds of creative content to answering your questions in an informative way, even if they are open-ended, challenging, or strange. Words in, words out. At their core, LLMs are essentially sophisticated pattern recognition machines. They excel at taking in strings of text and mapping them to corresponding outputs. When you input text into an LLM, it doesn't understand the words in the same way humans do. Instead, it breaks down your input into smaller units, often individual characters or words, and converts them into numerical representations called tokens. Think of these tokens as a secret code that the LLM uses to represent language. Each word, punctuation mark, or even a special character like a hashtag is assigned a unique numerical token. The LLM then processes these tokens, using its internal network of neurons and layers to decipher the meaning behind the sequence. Once the LLM has processed the input and generated an internal representation, it's time for the output. It uses a similar process in reverse, converting its numerical output back into human-readable text. The model predicts the most likely sequence of tokens that aligns with your input and the patterns it has learned during training. These tokens are then stitched back together, forming the words and sentences that make up the LLM's response.